Is Howard in here? I thought I saw him join, but then it looks like he
was, and it looked like he dropped.
Okay.
And I don't see Sandy or Jeff yet.
Yeah, I don't either.
So John, if they don't show or they come in late, you guys can swap their spot, and then we'll see if they make the last. Oh, there he is. Speak of the demo. Hey, Jeff, can you do a quick screen share just to make sure the functionality is good?
There you go. See it okay?
Yep.
Great.
Good to go.
Are we going in the order of?
Yeah, so Brian will be first,
Okay.
you'll be second, and then John and the gang will be last.
Perfect.
Can anyone hear me? Hello?
Yep. Hey, Howard.
Hey, sorry, I'm having great difficulties with my audio today, so I'm not getting any sound through my headset, but I am getting on my laptop, so it's going to be a little rough, but if you can hear me okay, I can take it from here.
Yeah, you're coming in clear.
Okay.
All right, 2-minute warning. Okay, good afternoon. Welcome to the second session of the 911 Special Interest Group. We have a jam-packed session of 3 speakers talking about various items and specifics related to 911 and how GIS is supporting vice versa. and I will pass it off to Brian Bond, who is with Yavapai County, talking about his workflow for dispatch mapping. Brian?
Hello. Thank you for joining. So weird, I hear something in the background, and so you hear myself. All right, sorry. This is going to be a short presentation, so I'm going to get started without an introduction. If it moves, come on, next slide. There we are. Did I miss that? There we are. So I'm introducing some technologies for the purpose of this discussion, such as sensors software to incorporate into future next generation 911 dispatch systems, or some systems may actually already be including these. Internet of Things, IoT, the definition is that a sensor or actuator assembled in a physical object that's linked through wire or wireless networks. These were invented back in 1999, initially to promote radio frequency ID technology. Something that really got me interested in the internet is those RFID tags. Those IoT devices really didn't become mainstream until 2010, 2011, according to one of my sources. Internet of Things for fire safety, such as smoke, carbon monoxide, motion, LPG, tank sensors. These are such systems for fire safety that can be used as tools, even for escape for a large multi-story building. Internet of Things is common for the automotive industry, such as OnStar that we're familiar with, Intune from Toyota, InSync from Ford, and even insurance companies like State Farm have auto telematics programs. We're familiar with wearable devices such as smartwatches and even smart clothes. I don't own any of those, but maybe one of you do. Hey, an early example of Internet of Things was in 1982. Is that right? 1982? Around that time, students from Carnegie Mellon University invented one of the earliest known devices connected, which was a Coca-Cola vending machine. So they knew they would save themselves the time of walking down to where it was when it was empty. So moving on to real-time devices. Real-time devices such as GPS devices and automatic vehicle locators, both for fleet and emergency vehicles. Even the use of social media posts can be real-time web-enabled sensors. And last, software as a service, or SaaS. Some examples such as ArcGIS Online, cloud applications, rapid deploy that we all have here. Intrado has a product. There's even fleet management vendor softwares. If you've used Office or even Google Docs, both could be considered software as a service. So I introduced those things, and we'll get back to them in one of the future slides, if I can advance my slide. All right, so let's moving back over to the GIS and in a dispatch system. This is a hypothetical slide because the majority of Arizona has not yet transitioned to supporting legacy and next generation yet. The information on this slide is only to show a trend, which I'm hoping will come about. But it's going to be dependent on technology, vendor solutions, legislation, and the 911 community adopting such things. I'm hypothetically showing the map of traditional shapefiles or the GIS data in the red bar on the, I guess it'd be on the leftmost screen you see, and I think my slide got cut off just a hair so you can't see the titles. So the rightmost set of bars, the 3 bars, where it says 81 is where most commonly we're using shapefiles for dispatch maps. And web services may be somewhat common, but not very common, as just as much as non-traditional. So then when we transition from legacy to next gen, it's the middle 3 bars, which I'm predicting the use of web services become more of a common, but not yet dominant. And then the third group on the rightmost is where you have full next generation mapping is predominant across Arizona, where I'm predicting the use of web services and non-traditional tools increases to the point that shapefiles aren't as used as often. Now, the purpose of this hypothetical chart is to show how GIS for 911 mapping needs to be prepared to transition to update dispatch mappings using shapefiles and other means to other things like web services or non-traditional. What I mean by non-traditional could be more like using software as a service or some technology that hasn't been yet mainstream or not even invented yet. The reason for adopting non-traditional mapping services is due to the migration of next generation systems that's not dependent on traditional private company phone company providers, but something like a voice over IP software vendor, where dispatching could be managed by a third party and supported in regions of 911 dispatch systems that are not managed by local county or state governments. Again, this is a means to give a perspective on what I'm mentioning in my presentation, and it will be based off of the powers that be that would adopt something like this. So I wanted to bring up what map services, web services, what I'm talking about here. I'm talking about the back end to use in a web environment. The illustration here is the dispatcher and dispatch map. The dispatch map is a client, and the GIS services are on the host or the server. And this simple diagram, what we have, what we do every day, like on this virtual conference, we're receiving and requesting information and receiving the information over the web. Web services send requests for an extent of the map. As a result, the image that's data sent back to the client is faster. I'll get into that more in a future slide. Web services process has not does not have to read the entire extent of the data, it's only the extent of the client's map. Web services are also tied to scales, set scales that have been deployed and standardized probably by Google, but the ESRI GIS community also has adopted those map scales. The properties of these web layers are tied to the groups of map scales to do displays and labeling. If you made any ArcGIS Online maps or familiar with those maps, you'd also be familiar with the scales. And I think I jumped slides, sorry. All right, so moving in, yes, I did. We'll move into benefits. So web services are distributed through the same information and going to different systems. That's a benefit. So they can be accessed from different places. Web services using the internet or HTTPS access, there's no media that's needed. You don't need a direct link to the GIS data. Shapefiles can also serve, so I'm comparing and contrasting. Shapefiles can also serve more than one application, but a dispatch map must be able to read that data. Shapefiles are pretty old and common nowadays, but not every system nowadays may be able to read those shapefiles anymore. For web services, it's easier to distribute to different types of devices, easier to display on mobile devices than traditional desktops at the same time. Some web services use public safety applications, potentially could be shared to the public by GIS vendors or providing external applications, again, distributing to many different users. Web applications are disconnected. from the actual data. A benefit is the ability to update that GIS data without having to take down the user interface, that dispatch map. Web applications are independent from the software or the versions of software. Shapefiles, when updating to a dispatch map, may need to be taken offline or restarted. Up-to-date data, GIS data is crucial, so having that downtime can slow things down. Performance, obviously. So my great little diagram of slow, average, and excellent. GIS maps on the user interface potentially is faster when accessing GIS data from a web service. The GIS features within the request may be returned to the client as an image instead of having to draw each point, line, and polygon like with shapefiles. The size of the data is not a bottleneck to the performance of the mapping applications, the user interface. Applications that read shapefiles read the entire file and then have to display it in the mapping application. Securability, so restricting people from accessing the services through levels of privileges. Tokens are identified by granting privileges to certain requests. Shapefiles are file-based. Their security is only through a file or network security. Additional benefits about web services. So when we're talking about Internet of Things, we can, you see OnStar or Telmetrics can provide integration of information to 911 dispatchers, such as the partnership with Rapid Deploy to OnStar. Fire safety devices such as smoke alarms, carbon monoxide detectors can provide details on a web interface to provide additional information to the 911 dispatchers. Even Amazon Alexa can be pre-programmed to call an emergency contact. Real-time sensors, flood gauges to help monitor areas when it's cut off for the first responders. The picture of the bridge, the water under the bridge where the flood gauge is there. So that bridge is clearly passable, but if it was to be inundated, flood gauge could be warned and the dispatchers would know that that route is cut off. Obviously, you need to have those automatic vehicle locators in part of your emergency vehicles so that you know where they are in relationship to that bridge, so they can tell them via the radio, can't go that route. So also there's social media posts as a real-time sensor that can be used to help see the number of occurrences from the public, to be able to see the results after an event for documentation. Also, weather stations are examples of real-time sensors to help with first responders. All of this, though, there is a technical component of those internet devices to the dispatch center that is not covered in this presentation. And last, software as a service, the ability in the pandemic to dispatch from home. That may have happened using software as a service. An example of Alexandria, Virginia, in 2020, which is documented. They used FirstNet to help communications centers do dispatching from home. And think about Rapid Deploy within Arizona. What might come of this new partnership, and what is the possibilities ahead using that? So let's balance back at why not to use shapefiles. Well, one thing is English language is best suited for shapefiles. It wasn't built for multiple languages. So it works only in the United States. Well, what about if you're in Canada and in the French-speaking section? Shapefiles may not work as well. The DBF file table makes use of shapefiles being less desirable because of the limitations. And here's some of the limitations. Field names can only be 10 characters. Field values can't store both date and time. There's a 2 gig file size limit. So then with the geometry, there's not an XY tolerance for spatial data. So it's a simple data type. Looking at another problem is shapefiles can take 3 to 5 times storage space than other formats, especially as web services. They're not taking that same amount. Field widths, limitations for numbers, floating, double, strings, and dates can be a challenge. Shapefile convention, file name conventions are the 8.3, so that there's 8 characters followed by a period, and the file type is the 3 characters. In the modern operating system that we are running off of, that restriction's not necessarily as noticeable or is an issue today, but some older software expects that file naming convention. New section here of words of caution when moving to web services, though. So some requirements that dispatch mapping systems that use web services, understanding the GIS preparations for a dispatch map. You need to understand there may be some additional fields or that need to be done for symbology, key attributes for labeling. Because in a web interface, if some of you have been familiar with, that web environment's not as friendly as a desktop environment, which shapefiles may have used. GIS data may not appear to be any different from the desktop applications reading those shapefiles, but how the web map works causes some additional preparation for those GIS fields. Taking the GIS data and publishing it to a web service, this also means you have to have additional hardware where the web services live. Remember the previous slide that there was a server and a client. What hardware is needed for that server to accept those web requests? Then in addition to that, you've got more security. You need to set those permissions. Those seem to be straightforward, but whom has access, but that's an additional task that you have to manage, which may be an issue. And then last, update workflow processes. Just like on any other systems, you need to have a workflow to keep the data fresh. That's no different from the other mapping systems that we're familiar with today. And I'm going to use this chance as a shameless plug to mention workflows to define for your agency to support updating any 911 systems. Do you have your workflows done yet? Additional things to be cautious about when using web services. GIS data like global IDs may need to be required to be able to use your applications on those mobile data terminals in vehicles, disconnected use. There's new requirements that change the way we've worked before, and you may not be familiar with them, so having to know how that works. Obviously, more hardware is needed, like I mentioned, which means you might need more internet bandwidth. So this could set up more, you could set up more servers, so you could have more distributed web servers. So that means you might need to have more data centers just for a web mapping application. Updating process, of course, it depends on where that server is. Within a closed network, like we're familiar with, accessing those web services to publish and update the data can be more restrictive. Some of you have experienced that, having to VPN into a network and to update a dispatch map. Yet that's maybe the same as it is today, so it may not be much of a new challenge, but it still takes human interaction for that data change and the GIS data to be reviewed with the map updates. Security for GIS technicians, that's not something that GIS technicians necessarily would be familiar with. So the learning curve can be a challenge. New hardware security, needing for web security certificates or SSL certificates may be needed to be installed. It's either an additional cost or even a skill set that maybe only the IT department has more familiarity installing and setting up. Relying more on levels of technology if we use web services versus shapefiles that sit on a dedicated hardware in a dispatch center can be much different. How I imagine the future in a closed next generation IP network having other web servers, hardware in this network is not any more work than having a dedicated dispatch desktop device deployed for all the dispatchers on a dispatch floor. Another disadvantage, though, is the internet or that IP network must be available to share those web services. The more that we build in automation workflows for this process, the quicker we can get those processes up to date. A few last slides. We need to talk about metadata with your web services. Unfortunately, I don't have time to do that, but Steve Whitney is going to talk about it later this week. I've not heard Steve Whitney's presentation, but I'm going to kick the metadata topic over to him and let him talk to you about it. So please hit that presentation on, I believe it's on Thursday, unless it changed. I don't have a prearranged topic to align with Steve's. It's just how the stars have aligned in the 2021 AGIC Symposium. For GIS data, having metadata attached helps identify about that data. It can be very helpful. See Steve Whitney's presentation about metadata. Thank you for your time, and I'm going to end this. And if you get to my slideshow, I do have some additional references in my notes for my sources and online resources for you. Thank you.
Thanks, Brian. Appreciate it. Steve has a question. If you can answer it in the C event, I would appreciate it. We'll move on to the next presentation. And we'll have Jeff Ledbetter and Sandy Dyre with Datamark. Jeff, if you can share your screen. Perfect.
All right, great. Hey, everybody. I'm glad to be with you today and talking about one of my favorite nerd topics in the world, 15 minutes with fishbone analysis today. So you've got me, Jeff Ledbetter, your friendly neighborhood GIS nerd. Here, I'm a public safety GIS expert with the Datamark team of Michael Baker International, and I've got with me for some color commentary my coworker Sandy Dyre. Say hi, Sandy. Oh, she's on mute. There you are.
Hey, hi, how are you? I'm sorry, Jeff. Caught me off guard on that one.
That's okay. All right, let's get right into the show here. So what are fishbones? Fishbones are really a data quality tool. And so I want to lay a little bit of foundation for data quality, and we can dive through this as we move forward. But data quality has, it can be characterized in many different ways, but the construct that I like the most has 5 dimensions of it, and it addresses availability, completeness, accuracy, timeliness, and consistency. And the fishbone, particularly for address points and road centerline normalization, really hits hard in that completeness and accuracy dimensions of data quality. Because it helps understand the relationship between the two data sets, and it helps find spots where normalization is an issue, where you don't have data that you need, which would be that completeness dimension, and where you have normalization issues with accuracy. So what is a fishbone? In terms of addressing GIS data quality, fishbone helps you identify and understand the cause of a system failure. And that is, the system failure may be that there is an address point in the wrong place, and that there's not an address point, that there's extra address points or address points that can't find its companion along the road centerline. In practical terms, it compares the placed address points, which are the points themselves, with the geocoded address location along the road centerline. It creates line geometry by connecting those 2 points. And it gives you a rich data set for comparison and analysis between the two data sets. And what you're really looking for spatially in the review of those Fishbones. I've got a little fly companion here with me that I'm not interested in being with, but the data set that is created, the geometry that's created, can be analyzed for primarily intersections. Intersection of fishbone to fishbone shows that there's some problem in the order of the place points, at least as it relates to the directionality of the road center line. An intersection of a fishbone with a road center line shows that there's some problem in the normalization of the attributes. Very often we see that there are some fat finger errors and directionals or street types and things like that that cause those intersections. In addition to that, it also gives you an easy piece of geometry to burn attributes onto where you find that there is some problem with normalization in either the address point data set or the road centerline data set. It tells a visual story, and it tells many stories actually, not just the ones where you find intersections or problems with normalization, but it tells the story of how you've ranged your roads. For instance, in this example, it shows kind of like slanting fishbones instead of more perpendicular fishbones that would demonstrate that there's probably a theoretical range on this road center line, and or maybe some range saving at the end, even if it's an actual range. Maybe they've saved some ranges up at the end, but in physical space they've been taken up, because it would show that the geocoded location of this particular address point is down here instead of right in front of it. Where you have more sort of perpendicular ish fishbones, you see that your road centerline address range is well spaced out, that it is showing the general location of the geocoded address is right on top and in front of where your place address is, and there's a good relationship there. You can analyze for these intersections, as I mentioned before, and find attribute mismatches to enforce normalization, integrity of normalization in your data sets. Some good examples of where fishbones tell stories that are interesting for GIS data quality is where you'll find a case where address points are not reflected in centerlines, road centerlines. This means it couldn't construct a fishbone. It didn't find the address on a road centerline that is located in your address points. This again occurs when you have these sort of fat finger attribute errors where streets are misspelled, inconsistent directionals are applied, inconsistent street types, or potentially road centerlines that should have been built but weren't, or road ranges, address road ranges that need to be extended but haven't been. Another good example is that misordered location of the address points, where you have, in this case, the directionality of the line, which you can't see here, but the directionality of the line, instead of being this way, is actually this way. 1501 to 1514 made sense, but there is a flipping of that order here with 1507 and 1511. Sometimes the addressing is poorly, just simply poorly addressed areas are reflected here, but the intersection of the fishbones tells you that there's something to check out here and see if there actually is an error to be fixed. Then they also tell, again, a very good visual story. When you find a collection of fishbones like this that kind of remind you of Keanu in The Matrix avoiding the bullet, dodging the bullet, you know that there's something wrong, and you know pretty quickly that this is actually a directionality problem of the road center line. And if you were to flip the geometry, all of these fishbones would probably line up in a very nice, more than likely, what am I trying to say, perpendicular-ish way. So you can see the geocoded points are just flipped. Oh, yep, made a bigger picture of that. Nice. Wow, that was way faster than 15 minutes. But I want to encourage everybody to take a look at Fishbones as a data quality method to examine the relationship between your address points and your road center lines. Sandy, bail me out. Give me some good color commentary here.
So anyone who knows me knows that I'm a big fan of Fishbones, not only for the reasons that Jeff identified, but that your Fishbones and the way and the results of the Fishbones can truly identify for you a good remediation method, right? So as you're running into Fishbones, you're going to find either the cross intersections that Jeff's talking about. You're going to find those very long Fishbones, which may be connecting your address point to, say, a center line that's completely on the other side of the county. It can also identify those address points that are not finding a road center line. Generally, by tackling your road center lines first, a lot of this may get solved, right? Because what Jeff identified here is that, yes, you may have address point issues, but you could, the overall problem could be road center lines. If by tackling your road center lines, checking your directionality, checking your ranges, those types of things, you may find that those address points, when you rerun your Fishbones, that they may align properly. If they don't, then we know that we have an address point problem. And some of those address point problems can be tackled. Others of them are not going to be able to. Why? Because historically, that's just the way it is in real life. And that's where you're going to want to go into your system, and you're going to exception those out to where those types of errors don't pop up again, right? We just know that's the way it is, and there's no way to fix that one. I think that road center lines, the actual Fishbones themselves can be highly informative, especially when you take your Fishbones and you're going to overlay your boundaries and see where those point placements and your road center lines themselves need additional segment breaks, right? To be able to fall within the right boundary, whether that's PSAP, law, fire, EMS, for proper routing scenarios. I don't know, Jeff, if that's the color that you were looking for, but that's what I was thinking as you were talking.
That's perfect color. As I said, it tells a visual story, and those are good examples of ways that it tells the story. So that's a quick review of Fishbones. Now, in terms of things like how did this get created? It's a complicated process that involves geocoding, that involves saving those locations and creating the geometry, and merging into those attributes where there may be some problems. So there's lots of ways you can do it. It can be done through products, through scripts, through manual effort even as well. But this visual story is one worth examining for these sort of inconsistencies and problems. And I want to make sure that everybody's aware of it as a data quality method. So appreciate the commentary there, Sandy. Appreciate the time and attention from the wonderful AGIC audience, and we'll yield the remainder of our time to the more complicated topic of address parsing.
So Jeff and Sandy, you have a question from Johanna down in Tucson. I'll read it off to you. Is it possible to mark exceptions in a Fishbone analysis, like topology exceptions, so you can run it on a regular basis and skip over the weird addressing you can't do anything about versus problems with the data?
Yeah, absolutely. So how you accomplish the creation and management of your Fishbones will provide the answer to your question, Johanna. The products that we create absolutely do that, and they'll mark an exception. And the next time, it's just not even going to ask the questions of that particular piece of geometry about Fishbones as it recreates them. But if you're creating these with scripts or your own tools or doing it manually, certainly it would be a wise thing to do to kind of set up a flag field in your schema that allows you to say, yes, accept this one, and then put into your logic as it analyzes the Fishbones to just ignore those that have a yes in the exception flag. So it's a good question and a good idea if you're doing it.
Awesome. Thanks, Jeff. Thanks, Sandy. Appreciate it, guys. If anything comes up, I'll read it to you, and you can either answer in the Q&A or we'll have time at the end. So Good, thanks again, appreciate it. I will kick it over to John, Howard, and Bo with Logistic and Terra Systems Southwest, talking about addressing.
Thanks, Eric. Hi, welcome to our session on intelligent street address management. My name's Howard Ward. I'm with Terra Systems Southwest, and I'll be joined today by Bo and John from Logistic Research, who have been the real workhorses in this process we're going to show today. I've been playing the role of the client, and they've been the tech support. Next. All right, so let's talk about, excuse me, let's talk about the need for a particular element of intelligent address management. That's address parsing. We've been collecting and processing and appending statewide address points and other data sets, but particularly address points for the last several years as part of our work with the state 911 office. These not only support 911, but they also support a number of other state business processes, and it's a very popular and important product. So hence the need for address parsing. That's part of the need. Let's go to the next one. The data that we collect from the 911 systems across the state comes in a variety of schemas with various levels of parsing involved. This is a chart down the left-hand side. You'll see a NINA NG911 address schema elements, the address element portion, and I've included a few columns from some of the 911 systems to show you how we map their fields to those schema. And you can see they're all a little different. These are pretty consistent with the NINA standard, but there are other systems that are a little more diverse when it comes to mapping to the field. So there is a wide variety of schemas out there we need to deal with. Next. Again, this is the target that we're aiming for. This is the NINA schema. We have 3 address number fields, a prefix, an integer address number, and a suffix. We have a pre-modifier, pre-direction, pre-type, pre-separator. We have a street name, finally. Whew, it took a while to get down there. And then we have post type, post type, post direction, post modification. So those are the standards. And then of course we have some different aggregation of elements in the legacy street name fields too. So it's a bit complex. Next. So what happens is that we go ahead and we take this data in and we clean it, we parse it, we standardize it. I'm using the royal we. This is the code that Bo and John have written. You can see the raw address that are on the left with punctuation that's removed in the cleaning process. You can see that it's parsed now into NINA standard fields. You'll also notice in this example, we included a parcel number in the address string, which isn't common in NG911, but it is in other business systems. So that capability has been included. And you finally see after parsing, it's standardized. So the STR street type has gone to a standard abbreviation street. And I will say that for NINA, this has changed and this would be spelled out street. The legacy field now will contain the ST. So this slide is a little out of date here. And then again, at the bottom, you can see the civic and the non-civic address portions. Next. The way this is implemented is as a script tool inside ArcGIS Pro, which accesses a web service on the Logistics server. Typically, we would go through and append all the address points for the state. Then we would look for common suffix types embedded in the street name field. So such things as AVE or ST or whatever. And once we find those, we'll take a look and see what the contributing organization was. And then we'll just assume that we should look at all the addresses coming in from that particular organization for potential parsing. We'll select them into a new feature class. We'll open this tool and put in the parameters you see there, an input feature class and a field, an output name and a location on our local disk. And we'll run that. And what it returns is a file geodatabase table with suggested parses. In some cases, it can't parse an address, in which case we'll manually fix it. And then we'll use a unique ID to join that fixed feature class back to the original and move the parsed information into the feature class, the final feature class. And with that, I'll turn the presentation over to Bo to pick up from there.
Thank you, Howard. And my name is Bo Guo from Logistic Research. And we are a bunch of really technical kind of type of person. And we were having trouble who should making this bragging about A3i, and nobody wants to do this shameless work. And later it turned out to be because bragging, my initials, the two of my initials, all in the word of bragging. So I end up taking care of this slide. But to be fair, the comparison is not quite relevant sometimes because A3i is not a geocoder, is not a parser per se. I don't think there's any existing genre of software that we are trying to achieve. It is, we call it a address analyzer. So in that sense, let's look at successful rate. We actually achieved for 99+% of parsing success and for any well-formed addresses, okay? And we do not do matching score because we think for next-gen 911, and any address with ambiguity is not a good thing. And it's about life and death situation. We want that to be, have a good deterministic result, being correct. We also provide the reason for parsing failures, okay? So above, essentially, we are talking about parsing opportunity, then the task of parsing. But there's another thing that A3i does is the standardization and local awareness standardization, for example, okay? And the local awareness, so if typical parse will not compare your place location name to be in the state or even in the county. Let's say we have 2 St. John's and 2 Cottonwood in the state. And we are going to be able to say, hey, your St. John, your Cottonwood is in this county versus the other county. So those location awareness is something built into it. Being able to do that simply because we have configurable rules for each individual state and for a PSAP or the providers to be able to configure the names, including place name and standard other legacy names. Certainly we have the standard set of NINA parts, the address component parts. So that's the standardization of that. In terms of performance, yeah, we were, earlier I said, we are pretty fast, but later I said, wait a minute, we really don't have anything to compare with. But we achieve reasonable performance through database indexing and also caching, and also some of database technologies, which I will talk about in next slide quickly. So the overall architecture is very simple. Essentially, you have the pre-process and post-process wrapping around the NLP, the AI engine, which is open source engine, and that constitutes backend. Then the database end, we have RBMS. Then the rest essentially hits the backend, which communicates and retrieving information from the database end. Next. So behind A3i address engine, we have essentially 3 pieces of technology. And one is the tokenization through regular expression, and which is very mature technology and widely used for tokenization processes and for pattern matching. Then the core of that, kind of like black box, is the natural language processing. And the advantage of that is we can be more adaptable by essentially making address trainings, going through address training rather than messing around with code logic. So that's, later John's gonna show some of that. Then another piece that we use, as I mentioned earlier, is the RBMS. It's a database, data-driven design, configurable tokens and aliases and standards. Talking about aliases, there might be different ways to spell a certain place names that you can customize it and adding those to be the alias to the standard name. Then when you get the result, your alias will be standardized to the one and only standard name. And performance, as I mentioned, about caching and table indexing, and there's a scalability, which essentially with RBMS, we can partition the database tables into multiple physical pieces, storage pieces, so that it can support not only as a statewide, but certainly nationwide or even internationalize it, because in that way you can scale. So with that, I'm handing this over to John.
Awesome. Thank you, Howard and Bo, for giving us some good background information there. Now we're going to kind of dive in there and talk a little bit more of specifics into how this parsing engine works. So one of the advantages that Bo kind of touched on to using our NLP processing and the relational database design is really the trainability and scalability of the engine. The training aspect allows us to correctly handle special cases where addresses don't conform to normal standards. In other cases, the training allows us to correct errant behavior in the parsing engine. For instance, we recently ran into an issue in which the parser failed to recognize zip code if it came before the state in this address position. In order to remedy this, we passed a set of training data into the parser's learning module, and we showed it what the expected outcome was. And this training happens through a really easy to use web interface. And then after training that, now our parsing engine recognizes a 5-digit zip code if it comes before or after a state. And then, kind of expanding on that, the adaptability of the NLP engine allows us to modify and train it for even more custom scenarios. So in this case, we're talking about something where we have Spanish language mixed in with English languages. So, it's widely known that any parsing engine that's trained on data sets from English languages only will fail miserably when you apply Spanish street names to this. So to remedy this, the A3i engine allows us to set up different projects containing different rule sets, and each project can be tailored to a specific address type. So we can set up a project for specific Spanish names to have a higher success rate on those versus a project that would handle really simple English addresses like Main Street better. Another advantage to the relational database is the ease of which we can configure and add domain validations. So as Bo kind of mentioned, this is not just a standard parser, but this really has multiple components. So it has the ability to geocode, it has the ability to parse, but it was designed for next generation 911 in mind. So it also has NG911 validation built in. And in order for a successful parse to happen, the system has to validate each parsed element against its associated domain table in the NG911 schema. In this case, based on Nina's street pre-type and street post-type domain registry, the value of Avenida is a valid value. However, the value of Avienda is not. And so in order to remedy this, it was identified in the statewide append that Avenida is a valid type within Arizona. And so we just added that value to our domain table. So now our domain table is slightly larger than the Nina domain table, but this is a valid value in Arizona. And so once we fix that domain table by just adding the value, then a parse successfully happens for that address of 113 West Avenida Lane. And it's really as simple as that. If we have a value that falls out, we can determine whether it's a true value that should be in there and add it in, and the next run it will parse successfully. And this goes in directly going back to NG911 and what Bo said. We don't want to have a matched score of addresses. We want to have a deterministic address setup. So it either is 100% a valid address or it's something that it needs to be looked at. So this kind of falls right in line with that. The next kind of cool thing in relation to the domain is what Bo was talking about, our locality awareness or our spatial awareness. Because we can configure domain rules, we actually have a list of all incorporated municipalities, all counties, and all states and their nested structure. So in the future slide, I'll show an example where we pass an address inside of Tampa, Arizona, and the parser engine rejects that because it knows Tampa is not a city or a county inside of Arizona. Another benefit here is our web services. So of course, I'm referring to our REST API, which is the primary method of interacting with the parsing engine. The REST API allows for fast, efficient access to the parsing engine, regardless of location. And some of the main benefits to using a REST API are that it can be scaled quickly, primarily due to the separation between the client and the server. Developers can also easily integrate with the REST API without much needed work, as we'll look at here in a second. The API is really, really lightweight because it relies on HTTP standards. And so most APIs are format agnostic, meaning you can use, XML, JSON, HTML, or other data interchange formats. In our case, our system uses JSON, and because it's so lightweight, it makes it incredibly fast for web access, which is really important for today's modern web-based world. And because the service communicates over HTTP, we can access it from any application capable of sending and receiving JSON. So it makes it incredibly powerful because we can embed it into web browsers, custom applications, ArcGIS Python tools. It could even be called from directly within FME, and really anywhere else where you can handle HTTP requests and look at JSON data. So as I just mentioned, the A3i API can be called anywhere you have web access and can handle JSON. And this does include from within ArcGIS Pro, as Howard mentioned. So to that effect, a need was identified for the ability to parse addresses directly from within ArcGIS Pro. And the reason for that is it lets people avoid having to go to a website, use an external application, parse their addresses, then download a CSV, and ultimately end up back inside of ArcGIS Pro where they started. So it kind of just makes sense if you can do it all inside of ArcGIS Pro that we would do that. And so to accomplish this, I created an ArcGIS Pro Python tool allowing users to submit a column of addresses from a table and receive the results directly in a new table inside of ArcGIS Pro. And I think Howard's actually going to be pretty excited about that because that's a relatively new change. Previously, we were creating a CSV. But I realized that creating a CSV output wasn't optimal because our users still had to take that CSV, import it into a file geodatabase to be able to do attribute queries and indexing to have more efficient joins. So that was one of the changes we just made here. And in terms of how this works, again, I mentioned we send addresses over JSON, and it's super simple. You pass in a feature class or a table that has a column of addresses. My script packages them up in JSON 1000 records at a time, sends them to the parsing engine. The results come back down, and it does that 1000 records at a time, as many batches as needed, and recombobulates the addresses back into a final table. And as Howard kind of showed you guys, this is what it looks like. This is the new tool that I gave Howard recently. And it's pretty simple. You choose a feature class, you choose your input field, then you choose the output table name, and this output name does have to meet the Esri geodatabase criteria, and I have put validations inside this tool, so if you try to name it something that can't be a geodatabase table, it doesn't even bother parsing, it just fails outright and tells you to name your table something else. Then you also choose an output location limited to geodatabases there. And then from there, you hit OK, it tells you how many batches are processing, what batch it's currently on, whether it succeeded or failed, and then gives you a detailed message of how many records were sent for each batch and how many records were returned and how long it took to parse these records here. And when we look at this inside of the ArcGIS Pro side of things, this is indicative of kind of what we would send an address. Because our system isn't just a parser, it's actually a geocoder as well as a validator. As Bo called it, an address analyzer. We do more than just validate or geocode or parse. The system expects addresses to be fully compliant and fully fleshed out. So there should be not only the house number, the full street name, but also the county or city it's in, as well as a zip code or a state. The more information you add to this, the better the parse results are going to be. But this is the results of that address being parsed. Our system returns the input address, which allows you to join the table back to the original table. It also returns these standard addresses for NINA and for legacy, NINA being spelled out and legacy being abbreviated. And additionally, we keep mentioning this location awareness, and I think it's a pretty cool aspect here. You can see that we didn't pass Arizona at all into our input address, but our system actually knew PNAL 85112 was in Arizona, and it returned Arizona as part of the standardized address because it was able to locate that. And again, it does parse everything into legacy and NINA. So we have, for each NINA or legacy abbreviation, we have its complementary fully spelled out value here. So it's pretty cool that we're able to standardize things like that. I think I've got about 6 minutes left, so I'll try and leave some time for questions, but let me just go ahead and hop over here. So we actually have a live demo set up. While I was working on creating the Python tool inside of ArcGIS Pro, my awesome coworkers have tackled the task of setting up a simple website allowing public access to the parsing API. The web UI allows everyone to test parsing for free. However, it does limit records to $50 or $50, 50 records at a time. For larger data sets, you know, you can contact us for more specifics, but the web UI does function the exact same on the back end as the Python tool. The only difference is it's outside of the Esri ecosystem and you can download CSV to join it. So it's pretty flexible. And with that, we're going to jump into the web UI really quick. And I put some addresses here for us to test and play around with. So here's the web UI. And as we mentioned a handful of times now, it is spatially aware. So if we were to pass these addresses and choose a different default state, it would actually become rejected because, you know, these are counties in Arizona. So we're going to go ahead and leave this set to default in Arizona, and we hit process. And it's pretty quick, especially if it's cached. So you can see we just got these results, and we can verify that these are accurate results. So we've got our successful parse code, our standardized address, which added Arizona because it knows it's here. And then we can look at the specifics and see that county road is the pre-type. Our street name is 3321. It's got our legacy pre-type. In this case, there's no difference between the NINA and legacy pre-types. And you know, we can keep going down here and look at this as well. So if we look at this address, we have eastbound. So we actually incorporated eastbound into our post direction domains. And so it's no longer just northeast, southeast, southwest, northwest, north, south, east, west. It also includes directionals for interstates and stuff like that. And then the last thing I want to show here in the web UI is our location validation. Again, even though it was rejected as an error and said this place isn't found, it's a missing place name, we are working on updating that error message to be more indicative of this place is not inside of this place. But it does fail. You get an error parse code. But the nice thing is that even though it failed, it couldn't validate, our system still parsed it. So even if you have a failed record for this location, it should still parse correctly and put its components inside of its appropriate places there. So that's all I have for the web UI. And then again, I was just going to show you guys a really quick sample inside of ArcGIS Pro, what it looks like. So we have our table here, a handful of addresses. We choose the feature class, choose our input field, our output name, location, and the state schema. We hit run. And because our public tool is limited to 50 records, there's no need for batch processing. So I've removed a bunch of code from this. There's not as many messages, not a ton of things happening here aside from it sending it.
I think you need a switch screen.
Oh, okay, thanks. Sorry about that, everyone. Give me a second. Okay, let's just do screen. There we go. Can you guys see the pro here?
Yeah.
Okay, cool. So again, we have this feature class, and it's just a selection set of our add Arizona. And we're going to pass 3 records in, just this full address, same things you saw, same parameters you saw in the slides here. We hit run. And again, I've removed a bunch of code that prompted messages and batch processing and records return and result return. This is really just to test and look at. It should take roughly 20 or 30 seconds here. And it's much less performant to build a geodatabase table than an output CSV. But as you can see, it took a few seconds, and we have a table here that we can run attribute queries on, table joins to, build indexes, really whatever we need to do, all inside of the ArcGIS ecosystem. And with that, I don't have anything else, so I'll go ahead and quit sharing. And hopefully you guys found that interesting.
Awesome, thanks, John. That was impressive. I know you guys have been doing a lot of work on building out the functionalities of some of these tools to automate the I guess you could call it more of the manual intensive workflows. So definitely that seems pretty exciting.
I got one question in the chat, Eric, if I can just do this really quick.
Yeah.
1, 2,
Go for
3, state route 60, I believe is what they asked for. And I didn't pass a place name, so it fails, but it is a pre-type. State route does come up as a pre-type. So I'm not sure who asked that, but it is a pre-type, not a street name.
And John, can you put that link? I'll throw it in the chat for the unless
Sure.
you want to throw it in yourself.
I don't have that web page open. I actually have it open on my laptop in front of me, but they're disconnected, so I can't paste the link over.
So
Yeah.
the chat is actually closed. It just closed. So.
Gotcha.
Okay. Very good. Thank you all. That was very informative. Definitely look forward to seeing more come out of that. And with that, that wraps up the afternoon session for the 911 Special Interest Group. Feel free to